All right, so in this segment, what we're going to do is solve an example problem applying Buckingham pi. We've looked at the techniques. That's what we did in the last segment, the step-by-step. There are 6 steps for doing Buckingham pi analysis. And what this does is it provides a mechanism by which we can take the parameters or variables that we might have in an experiment, and we can collapse them into non-dimensional groups. And then you can use those to be able to collapse your data and plan your experiments. So we're going to return to the very first thing that we looked at the beginning of this lecture, which was the problem of a drag, or of computing, or measuring, I should say, drag on a sphere. And if you recall, that was the one where we said that we would have to do 10 to the 4 or 10,000 experiments in order to determine what the relationship of the drag on a sphere is. And that makes no sense whatsoever. And so what we are going to do is come up with the pi variables, or the non-dimensional groups that characterize drag on a sphere. And so we talked about the main variables or parameters. We had force on the sphere. We had density of the gas flowing over it or of the liquid, velocity, diameter, and then our dynamic viscosity. And what we want to do in this problem, we are asked to find a set of dimensionless groups. So we will use the Buckingham pi technique. Let's go step by step. So those are the parameters. We see n is equal to 5, and that's the number of parameters for the problem that we're investigating. The primary dimensions for this problem, we don't have temperature, so we don't have to worry about theta for temperature. All we have, if you look at all the dimensions of each of the terms, which theoretically I should write out, but I'm not going to. Actually, I'll do that in the next step. But we have mass, we have length, and we have time. So with that, we have 3 primary dimensions. The next step here, looking at our primary dimensions, so force, we can rewrite that as mass, length, time squared. Velocity is length per unit time. Diameter is a length. Density is mass per length cubed. And viscosity, that is mass per length time. So there we can see we have R equals 3 primary dimensions. Because all we see in here is mass, length, and time. So with that, step 4 is to come up with repeating parameters, and we should have m equals r equals 3 repeating parameters. And these are parameters that will reappear in our different non-dimensional groups that we come up with. And for fluid mechanics, quite often good ones to use are the density, the velocity, and the diameter. And people have done this over and over and over, and then they conducted the experiments. And so that's how they're able to know that these are good ones. The same sort of thing in turbo machinery. You go through Buckingham pi analysis, and there are certain ones that you would pick. But that comes through practice, so don't get too worried about how we picked rho, v, and d. It just turns out that they're good ones for fluid mechanics. And then step 5 is the process of coming up with our dimensionless groups. So we have n minus m is equal to 5 minus 3 equals 2. So that tells us that we should have 2 dimensionless groups resulting through this process. And what we have, we said that each of those is going to consist of rho vd, and so we combine it with the remaining variables or parameters. So one of them is going to have force, rho vd, and the other one is going to have viscosity, rho vd. So those are the basis for our 2 dimensionless groups. and we'll cluster those together and come up with a dimensionless number. Currently they're dimensional, but we have to come up with exponents for that. So let's look at the process of making this dimensionless. So what I should do is correct that. I said dimensional, but at that stage they're really dimensional, because if I was to combine those in that form, they would have dimensions, and we want to make them dimensionless. That's what we're doing now. So pi 1, this will be our first pi parameter, and we take our force. And the technique that we do, leave your first variable or parameter as is, and then raise the other ones to different exponents. So density will be raised to the A, velocity B, diameter to the C. And this is then going to result in, and I'm going to pull in the dimensions for each of the terms that we have in this group. So we have that, and we've raised it to powers A, B, and C. We want to equate this to mass, we want to have 0 dimensions, length, we want to have 0 dimensions, and time, we want to have 0 dimensions. So we're going to get 3 equations, 3 unknowns, and this is the fun part of Buckingham pi analysis, is solving these equations. So we take our mass, and when we look at the mass term, and what you do is you look at all of the contributions to mass that are on the left, and you equate it to 0 on the right. We get a 1 plus an A is equal to 0, and that tells us right off the bat that A is equal to minus 1. And then we go to length. And for length, we have 1 minus a 3A for the second one, and then we have a B, and then we have a C. So that one's going to remain a little inconclusive because we still have a little bit of work to do. So let's park that for now, and let's look at time, which is the third. So on the left-hand side, we have a minus 2, and then the next place that time appears is in this term. So we have a minus B, and then that's on the right-hand side equal to 0. So that tells us that B is equal to minus 2. So that's a little bit more information. Now what we can do is we can take the A and the B and plug it into our L equation. So let's go ahead and do that. And from that, we can solve for C. And we get C is equal to minus 2. So the pi group, pi 1, the one with the force, turns out to be the following. We have force, and then density is to the power minus 1, so we have density in the denominator. Velocity is to the minus 2, so we have velocity squared in the denominator, and then the diameter is raised to the power minus 2. And so we have d squared. So that's what we get for our pi 1 group. And we'll check that, but that should be dimensionless. So let's continue on to pi 2. So what we're going to do, we're going to continue using the same base that we had here, but we're going to interchange f, and we're going to put in the dynamic viscosity in order to get pi 2. So looking at pi 2, again, I'm going to go through the process of raising these to some unknown power at this point. And our process is determining what A, B, and C is. So let's expand that out.